Just in time for our last class, we get this in yesterday's New York Times and all over the rest of the media. New planet. Could be Earth-like. You know, every time they get a new planet, it's always Earth-like. But this one might really be true. It was found by the standard Doppler shift method, which you guys all remember, and turns out to be the lowest mass planet that's been discovered in that particular way. And so as a kind of final farewell calculation, I thought we'd check the New York Times' numbers on this. You can go back and read the article for yourself. The information given there is that the orbital period is about 13 days. The distance between the planet and its star, that's the semi-major axis, is given as 7 million miles. These are, of course, not the world's best set of units. The distance to the system is 20 light years. That's really close. Somebody's quoted in the article as saying, you know, we could go there. Not so much. And I looked up the apparent magnitude of this star, which turns out to be about 10.5. And so, what can we do with information of this kind? Well, let's first put this into some kind of sane set of units here. 13 days is something, let's see, 3 days is 3.5 days would be 1% of a year. So this is like 3 times 10 to the minus 2 of a year. 7 million miles, that's something like 10 million kilometers. 10 to the 7 kilometers, which is 10 to the 10 meters. So that's something like 7 times 10 to the minus 2 astronomical units. And you know right away what to do with that, or at least you will if you go back in your notes for a few months. This is in good units to use a cubed equals p squared m. M then shows up in solar masses. So let's figure out the mass of this star. Let's see, 7 times 10 to the minus 2 cubed divided by 3 times 10 to the minus 2 squared. That'll be the mass in solar masses. 7 times 7 is 50, times 7 is 350, times 10 to the minus 6 over 10 times 10 to the minus 4. That's 35 times 10 to the minus 2.35, which is a third. Okay, so this star is a third of the mass of the sun, a perfectly respectable mass for a star to be. And then, let's see, let's do something else. It's 20 light years away. 20 light years. That's something like 6 parsecs. So it's really nearby. As these things go, not that you would want to take a spaceship and go there or anything, but it is one of the closer stars. And then we can do this thing. We can figure out the absolute magnitude of this star. I had written down the apparent magnitude. So that's that equation. Let's see, 5 times the log of 6/10. Let's call that 2 times 3 times 10 to the minus 1. Yeah, that's 6/10. 5. And then, you know this thing about logs. If you multiply them inside the bracket, you can add them outside the bracket. So this is log of 2 plus log of 3 plus log of 10 to the minus 1. Log of 10 to the minus 1 is minus 1. The other two I happen to know. The log of 2 is 0.3. The log of 3 is 0.5 minus 1. That's 5 times minus 0.2 is minus 1. And so 10.5 minus the absolute magnitude minus 1. Let's see, how's this going to work? This has to go over there. That has to come over here. Absolute magnitude 11.5. Now you may remember that the sun has a magnitude, an absolute magnitude of around 5. So this is much, much fainter than the sun. That's good, because it's less massive than the sun, and low-mass stars get faint really quickly. How much fainter? Well, we know how to do that, right? Let's see, that looks in the easiest format, it looks like this. m star minus m sun is equal to b star over b sun. I guess a minus sign out in front here, yes. So that's 10 to the minus 2/5, 11.5 minus 5, which is equal to 10 to the minus 2/5 of 6.5. All right, what are we going to do about that? 6.5 over 65 over 5 is 13. So this is 10 to the minus 1.3 times 2, 2.6. You could work it out. And that, in turn, is equal to, remember, this is b star over b sun, brightness of the star over brightness of the sun. That's 10 to the 0.4 times 10 to the minus 3. 3 plus minus 3 plus 0.4 minus 2.6. And that's, I don't know what, 2.5, I'd guess, times 10 to the minus 3. A tiny fraction of the brightness of the sun, less than 1% as bright as the sun. And this is the importance of the discovery, because it's in a 13-day orbit. It's really quite close to the star. We figured out how close. It's 7% the distance of the Earth to the sun is this planet from its star. But the star's much fainter too. And so if you do the little calculation, which is quite straightforward to do, we won't do it here, of how much energy this planet receives from its star compared to the amount of energy that the Earth receives from the sun, you get almost exactly the same answer. So here is a planet whose surface temperature is likely to be quite similar to that of Earth. Here is a planet where liquid water could exist. Now, we don't actually know that much about this planet except for its mass. It's 5 times the mass of the sun. 5 times the mass of the Earth. That could be either a big Earth or a small Neptune. And those are quite different objects, and we don't really know what category from that point of view it's in. It seems unlikely that it would be a big Earth because this is a low-mass star. It's also, as it turns out, a low-metallicity star. So it's got only a third the stuff of the sun, and it's got less than half the frequency of heavy materials as the sun. And so it's hard to imagine it could build up a rocky planet 5 times bigger than the Earth, but you never know. Stranger things than that have happened, and will probably happen again in astronomy, so you don't know what will happen with this one. There's rumors going around, I should say, that there are even more entertaining planets going to be announced in the next few weeks. So keep your eye on the newspapers. There may, in fact, be more to come. Okay, so that's the last calculation here. And you just never know when these things will show up in the newspaper. Okay, what we're going to do on Monday and Tuesday, we're going to do this double strength section. Sorry? Monday and Wednesday, thank you. We decided not to do the Tuesday one. We've got you guys all sectioned. I think there was an email yesterday which told you what section you're in. If you have any problems with that, make sure we know about it in advance. And later, well, probably Saturday or so, I will post 3 pages of instructions. You don't have to read them particularly carefully, but I would like you to download them and print them and to bring them with you to the class. Let me take you through the first page of this. Here we go, Cosmology, the game. And let me just take you through the sequence of play so you know approximately what will happen. So at the start of the game, everybody gets a role. You can be a junior or senior scientist at one of several competing scientific institutions or a member of the review committee that decides which projects to do. Each of the competing institutions then proposes a project and a funding request. The senior scientist has to present the case. The review committee then gets to decide. And so you can't do all of them. You can only do some of them. So the review committee decides what projects to approve, and they give either partial or full funding. And then they report why they have made the decisions they make. And then we tell you what the results of that scientific exploration is. So, you know, you go out and you try and find more supernovae, and we tell you that, I don't know what happens, magically all the supernovae have disappeared, or they're all way, way, way too bright, or whatever it is that the answer turns out to be. And then you know a little bit more about the universe. At that point, the review committee, which is made up of aging pundits, all die off. The senior scientists are promoted to the review committee. The junior scientists are promoted to senior scientists, and the review committee are reborn as junior scientists or something like that. And so we sort of cycle through all the roles, and you keep going through these cycles until you figure out what the dark matter and what the dark energy is. And then at the end, we will sort of debrief and decide what the key moment of discovery was and award a suitable simulation of the Nobel Prize. It was M&M's last year. We'll see. So that's approximately what's going to happen. And the key thing is, what kind of projects can you propose? And the other 2 pages of this handout are going to be a list of potential projects that you can propose. You can also propose anything else you can think of. And we will invent results on the spot for any other kinds of projects that get approved as well. But I figured it would be a good idea for you to have at least a range of possibilities of things you might consider proposing and why. So that will be posted on Saturday. My experience is that in just under 2 hours, you can figure out all the secrets of the universe in this particular way. Well, of a universe that I design, which is, you know, not as sophisticated, perhaps, as the real universe will turn out to be. OK, procedural questions on any of that? Yes?
So the universe that we're looking at isn't going to be like the actual universe. It's going to have different things.
Who knows? Since I don't know what the actual universe is, it would be a little hard to give you the actual universe as an exercise. What I have done is I have invented a universe which is consistent with everything we know now and has many more answers than we know now. I would be very, very fortunate indeed if that turned out to have anything to do with the real universe. So I wish it were true that I had those kinds of powers. But it's possible. That's the key. Other questions? OK, so last time we ended on kind of an optimistic note. I had written down this plot, which was a plot of omega lambda versus omega matter, going from 0 to 1 and beyond. And I put down, I showed you the plot of 3 lines on this plot, which is the lines indicated by different kinds of cosmological observations. So the supernovae, which we've talked about a lot, force you to be on a line something like that in the plot. So this is where the supernovae observation kind of forces you to be. And then the observations of the cosmic microwave background force the sum of these 2 quantities to be 1. And so you end up with something that looks like that from the cosmic microwave background. And then by comparing simulations of the growth of clustering to the actual clusters of galaxies that we observe in the universe, there turns out to be a 3rd line, and it looks like this. So this comes from clustering. Is that legible? Close enough. OK. And so the great thing about this was, if you will recall, that there were 3 different lines on a 2-dimensional graph, and they all cross at the same point. And this constitutes a test of the theory, because it is not necessarily true that if you put down 3 lines at random in a 2-dimensional space that they will all cross at the same point. And so the fact that they do makes you think that something about how we understand what's going on is going pretty much right, because there's no reason for these things to cross at a point. We predict that they do, because they're all measuring the same universe, but in different ways. And so the fact that they do lends some credence to this whole wonderful set of stories. But there's another way of looking at this plot, which is to look at what these axes are. What are we actually plotting on this plot? This omega that shows up is the ratio of the density of something to the critical density of the universe. So this axis is effectively the density of the dark matter. And this axis here is the density of the dark energy. So what we are plotting in this wonderful plot where everything works out so nicely is the density of something we don't know anything about versus the density of some other thing that we don't know anything about. And so in a certain sense, the fact that we're working, regardless of where the lines are, the fact that we've got these two axes means we don't have any idea what's going on. So that's perhaps the more pessimistic view. You know, thinking about this, you get a kind of faint odor of epicycles. Remember epicycles? Epicycles I talked about in the very first class, the very first lecture of this class. This was this business back in the Middle Ages where they thought the Earth was still the center of the universe, and they were trying to figure out what was going on with the orbits of the planets. And they discovered that a single circle for each planet didn't do the job. It didn't concord with what the observations were. So they said, all right, well, we know the Earth's the center of the universe, and we know everything has to be circles, so we'll put circles on top of circles. And then they were able to match the observations. But then the observations got better, and they had to have ever more complicated circles on top of circles. So so that was the story of epicycles back in the Middle Ages. And then, of course, what it turned out is that the idea that the Earth was the center of the universe and the idea that everything goes in circles are just wrong. And as soon as you abandon those two ideas and have the idea that the planets go in ellipses around the sun, all of a sudden everything gets much simpler and it's all explained. Well, so what's happening in cosmology now? We're observing the motions of galaxies and of objects within galaxies like supernovae that we can see. And the first thing we found out is that the rotation of galaxies and other indicators of matter aren't in accord with what we expect, so we invent dark matter to explain the internal motions of galaxies and galaxy clusters. We then discover that the external motion, the motion of these things through the universe, also doesn't accord with what we would have expected, so we invent dark energy in order to explain that. So we've now, in the past 25 years, invented two different but completely imaginary, as far as we know, concepts to fill 96% of the universe with to figure out what's going on with the fact that the motions we observe are not the motions we expect. How many more? Let's go out and measure some more things. Then maybe we'll need dark something else. And dark something else after that. And maybe it needs to change with time. And maybe it needs to magically appear halfway through the history of the universe or something like that. Who knows? If you keep inventing these things, of course you can explain anything you like. Just in exactly the same way that if you have enough epicycles, you can have a model with the Earth at the center of the universe that explains all the motions of the planets you see. If you get to just keep inventing words here, of course you can explain the universe. And what would have happened if this line didn't come across? Supposing that line had been out there, what would you have done? What you would have said is, well, of course, we don't understand dark energy, so we've just proved that dark energy varies with time, or varies spatially, or becomes opaque at large distances, or some other quality, and then we would have rewritten this graph so that they do cross. That's not very compelling. And indeed, it has gotten sufficiently embarrassing that there is now just beginning to be a feeling that maybe what's going on is we need new laws of physics. Maybe we're at a moment like the end of the 60th century or the end of the 19th century where the current basic ideas that we base our theories of the universe are about to be radically transformed. That's possible. It's also possible, that we'll wake up 3 years from now and see in the newspaper that someone has discovered what the dark matter is. And that 3 years after that, we will wake up and read in the newspaper that some scientists have developed a good string theory that entirely predicts exactly how the dark energy is going to behave. I think in general, it's always a good idea to bet on standard physics rather than revolutionary new ideas. But if you keep at it for a quarter of a century, as we have in looking for the dark matter, and keep finding nothing, you got to start to wonder. And indeed, there was a radical theory proposed a few years back about the dark matter in particular, that there is no dark matter. It's just we don't understand the laws of gravity. And so, we had to modify the laws of gravity for very high gravitational fields. That turned out to be relativity. And they suggested that you also need to modify the laws of gravity for very low gravitational fields, the kinds of things you feel at the edge of a galaxy from the galaxy. And they figured out how you would have to do that in order to explain the orbits of galaxies without using any dark matter. This is called MOND, for Modified Newtonian Dynamics. And I don't think it's become clear that that particular theory probably isn't going to go anywhere for various reasons. It doesn't seem to be self-consistent. But nevertheless, this was seriously proposed. It was also, I have to say, a little philosophically dubious, because if you want a new theory of gravity, you don't want to go back to Newton and start over again. You probably want to start with relativity and move on. But they made it consistent with relativity. They worked out all the stuff, and it seemed to work okay, except it turns out it disagrees with observations also. But it was a real attempt to imagine that these things might really turn out to be epicycles. And if there isn't progress in finding out what's going on, I think we're going to see more of that as time goes on. And it may be that in 50 years, these things will look like what we think about people who thought that the Earth was the center of the universe. So we'll see. Now, there is one additional thing that we know about the universe, in addition to these three lines, which are kind of the basic information that we currently have. And that is, so here's another fact about the universe, kind of an obvious one. The fact is that we exist. Otherwise, we wouldn't be having this conversation, right? And what does that tell you about the universe? It tells you the fact that life exists, and in particular, what we grandiosely refer to as intelligent life exists. Let's see. What do you require the universe to have if life is going to exist? It needs a couple of things. Even, and we can get into a whole argument about life as we know it, and whether you can make it out of silicon instead of out of carbon, or whether you can have life made entirely out of neutrons on the surface of a neutron star or something like that. But no matter how you slice it, it's got to have some complexity to it. You've got to have a lot of moving parts, one way or another. You have to have information flowing back and forth. You can't make a living creature out of nothing but helium atoms. Helium, you may remember from chemistry, is a noble gas. It doesn't interact. It can't form structures. And if you had nothing but helium, there would certainly be no life, because there'd just be a bunch of helium atoms that don't interact with each other. If you made the universe entirely out of WIMPs, weakly interacting massive particles that just kind of fly past each other and don't pay any attention to each other, you're not going to have anything like life, because there's no complexity. It probably also needs some time to evolve. It took a while. If you start, there's this wonderful experiment where you take a whole bunch of stuff that was supposed to be in the oceans of the early Earth, and you put it in an atmosphere of carbon dioxide, and you keep sending electricity through it, simulating lightning strikes. If you keep at that for long enough, you can make things that seem like some of the simpler amino acids. So you just keep flashing lightning at the ocean, and you hope that eventually you build up life. Maybe yes, maybe no, but certainly it takes a long time. And once you have somehow magically out of this process self-replicating viruses or something like that, then you got to stick around for a few billion years while evolution takes hold and makes bigger and bigger and more complex structures. So you have to have a certain amount of time to allow this process to go forward. For example, supposing it were true that omega lambda, that's the density of the dark energy, was great, instead of being around 0.7, was greater than 100. So the whole universe is being pushed apart by this stuff, and there's hundreds of times more of it than there is in the current universe. You're not going to form any structure. We looked at the formation of structure last time. You just push the universe apart really fast, And you never get galaxies or stars or anything like that because there's too much dark energy to let them congeal. So push universe apart, no structure. So that would be a universe that's very unlikely to have any kind of complexity and any kind of life because you just take all these individual particles and push them far away from each other. Supposing it were true that the density of matter is significantly less than 10 to the minus 2. So instead of having a third the critical density, it has less than 1% of the critical density. Then you've got nothing to form the structures with. And so the same thing happens. Also, no structure. On the other hand, if the matter density is way up about in the thousands or the millions in this kind of scale, then everything collapses right away back into a black hole. And again, there isn't a lot of structure in a black hole. It's one single point in the center of the event horizon. So we have no way of knowing what these numbers should be, but what we do know is that we are fortunate that they happen to be in the relatively narrow range, because if they weren't, we wouldn't exist. This turns out to be true of most of the constants of nature. For example, here's another example, the Schwarzschild radius. Remember the Schwarzschild radius, the event horizon of a black hole, given by 2gm over c squared. Now, supposing you lived in a universe in which g, the constant of gravity, was substantially bigger than it is in our universe. If g were bigger, and supposing you, in that same universe, c, the speed of light, were a good deal smaller than it is in our universe. Just pick some other values out of a hat such that this is true. Then the Schwarzschild radius associated with any given mass would be bigger, because both g is bigger, c is bigger, and then for the same amount of mass you get a big Schwarzschild radius. So now think about what happens if the Schwarzschild radius is bigger than the radius of a white dwarf. Then you never get white dwarfs or neutron stars. You go all stars evolve when they run out of nuclear fuel straight into black holes. Then all stars end as black holes. And the consequence of that is that the carbon that is made in stars is never dispersed into the universe, and you never end up with planets, because the next generation of stars is still made out of pure hydrogen and helium, just like the first generation of stars was, and you never end up with enough heavy elements, with any heavy elements, and so you can't form planets. So no carbon or anything other than hydrogen and helium. And you're not going to make life out of hydrogen gas and helium. Now, carbon, of course, this fabulous substance, does all this wonderful chemistry. It forms rings, does all this great stuff. That's why organic chemistry, which is the chemistry of carbon, is more complicated than the whole rest of all the other elements, chemistry of all the other elements put together. And so the properties of carbon are very, very important for allowing complex structures to exist. So properties of carbon, and it turns out that if you vary would disappear or not be able to support these complex chains and complex carbon chemistry would disappear if the constants of nature, and in particular something called the fine structure constant, was even slightly different. It also turns out you couldn't make the carbon in the first place, because there's a property of the way the energy levels work in an atom that allows the reaction of 3 helium atoms to fuse into a carbon atom to occur fast enough for that reaction to actually take place by substantial amounts. So it wouldn't take much messing around with the constants of nature to make carbon either not exist or have different kinds of properties. You know, if carbon turns out to be just like iron and it just kind of sits there, you're again going to have some trouble creating any kind of complex life. So we have this odd situation in which it appears that drastic, really quite drastic fine-tuning of natural constants is a prerequisite for life. So not any set of constants will do. In fact, if you picked a random bunch of numbers for all these constants, almost certainly that would be a universe with no complexity in it at all. And this gives rise to a set of ideas called generally the Anthropic Principle, which is kind of the idea that the fact that life exists, and people in particular, is important for understanding physics, for understanding basic physics. And the way I've just stated that, that seems kind of obvious, right? Of course it has to be true that the universe is such that we can exist because we know we exist and we're the ones who are studying the universe. And so just in that form, it's not very interesting, but the implications of it lead you in a wide variety of different philosophical directions. So the question is, why do all these constants, G, C, lambda, what have you, have the values they do? Okay, so as I said, there are a wide variety of different kinds of categories of answers to this. One is that it's just a big accident. Whatever it was that set these numbers happened to pick a set of numbers that allowed life to exist. And there's nothing to talk about because it's just a complete accident. And it could just as easily have picked out some other numbers, and even though most sets of numbers don't allow for the existence of life, the set of numbers that were somehow determined by whatever mechanism determined them, just kind of by accident produced a set of numbers that allows complexity to exist. Not very satisfying approach, because among other things, if that's true, your thinking stops dead right at that point. If you can attribute everything to accident, you just go on with your life. Another sort of the opposite of this is to say it happened on purpose. Life created, if you want to use that term, or the constants of nature that allow life to exist are created on purpose. And there's, an obvious religious subcategory here, where you say that there is a creator, a god of some kind who did this on purpose. So this leads to various kinds of religious explanations, but in more general terms, and it doesn't have to be religious, this is what's called the strong anthropic principle. Which says that for some reason, be it religion or anything else, that the universe must have life, or have the set of constants that allows life to exist. One of the things that the physicists are trying to do is to figure out why these numbers have the values they do. Maybe it turns out that if you finally work out the final theory of physics and everything, that will tell you what these numbers have to be. And there's only one choice, that you can't choose randomly from these numbers, that there's some theory that underlies it that requires you to pick certain numbers, and that those numbers in turn require the existence of life. And whether or not you attribute that to religious causes, it doesn't make a difference to the sort of structure of this kind of argument, that there's only one way you could have made the universe. Somebody phrased this, it might have been Einstein, I don't remember, phrased it as, the question is, did God have a choice? Could you have made a self-consistent universe with some other set of numbers? Maybe not. But the approach to this, which is getting the most attention at the moment by the kinds of people who think about these things, is the concept of the multiverse. Universe is one universe. Multiverse is many. So the idea is that there are many universes with different sets of constants, sets of numbers and laws. Well, if that's true, then things are pretty straightforward. If you've got 100 jillion universes out there, and each one has a different set of laws, a different manifestation of the laws of nature, then it's not surprising that the one we live in happens to be conducive for our existence, because there's a whole bunch of other ones out there that there are no people in. And naturally, we exist in the one case where we can. You know how this works? It's like going out into a parking lot and you see a license plate out in the parking lot, and the license plate is 308BJ6 or something like that. And you say, gosh, what a coincidence. Out of all the license plates in the universe, that one happens to be sitting right in front of my office. But of course, if it was any other license plate, you would have said the same thing. And so that's actually not surprising. So similarly, if you have a whole lot of cars of universes in the world, there are a whole lot of cars in the world, right? There's billions of cars in the world. What are the odds that you get into the one you own? Well, pretty high, right? Because you're doing it on purpose. Similarly, if there's lots and lots of different universes, each one with a different set of physics, what are the odds that we exist in one that allows us to exist? Pretty high. But the question is, where do all these universes come from? And so how do you generate many different universes? Why wouldn't you be satisfied with just having the one you've got? And so again, there are a number of different subcategories here. There's the one in which you look beyond the cosmic horizon. Now, the cosmic horizon, you know, if the universe is 13.7 billion years old, we can't see anything more than 13.7 billion light years away. And in fact, the further away we look back in time, so we certainly don't know anything about what something 15 billion light years away is doing now. And so you can imagine that there are kind of slow changes in the constants and laws of nature, and that by the time you're 100 billion light years away from us, that part of the universe, which is causally disconnected from our own, has some other kind of physics that is going on. And so you postulate an infinite universe of which we can only detect ever, in principle, a tiny fraction. And over there somewhere, there's another set of constants going on. And so there's another set of physics far away that we know nothing about. And so that's one option. Another option is other dimensions. Those of you who have read any of the popular accounts of string theory may be aware that one of the problems, or perhaps advantages, well, the computer scientists call these features of string theory, is that you require either 9 or 10 or 11 or perhaps 26 spatial dimensions in order to make it work out. Then they do this clever thing where they say, of course, we live in a 3-dimensional universe, but it's really a 10-dimensional universe with 7 dimensions rolled up so tight you can't see them. Kind of a dubious proposition, but it actually works out quite well mathematically. But you can imagine that you're in a 2-dimensional universe, and here's your universe, but it's embedded inside some additional spatial dimension. There could be another 2-dimensional universe down here, and you would have no way of interacting with it. And so you can imagine that these extra dimensions that are being postulated allow the existence of many different 3-dimensional universes kind of next to each other, spread out in these higher dimensions. And perhaps they don't all have to be 3-dimensional universes. They can be other kinds of, I mean, that's another crucial number, right? Is how many spatial dimensions your universe has. And so one could imagine that these kind of extra dimensions, talked about quite seriously by the string theorists, allow the existence of many different universes with different physical laws to choose from. There's also a kind of evolutionary argument. This is presented in a popular book by a guy named Lee Smolin, which is a wonderful book. One should read it. His thought is that each time, and this came up, I think, earlier in the class, each time you make a black hole inside the event horizon, a new universe forms. So that's one way of doing this. So new universes form from old ones, from black holes or whatever. And supposing you postulate that each daughter universe has slightly different parameters, but only slightly different from its parent in the way that each of us has a genetic material that's closely related but not identical to that of each of our parents. Well, what happens? You then favor, in the idea that you make them out of black holes, you favor universes that produce lots of black holes. And so there's a kind of survival of the fittest, not just for organisms, but for whole universes. If you're the kind of universe that produces lots of black holes, you're going to have lots of children. Then after this goes on for a long time, most of the universes in the multiverse will be the kinds of universes that produce lots of black holes. How do you make black holes? You make the most black holes by producing lots and lots and lots of stars. Stars are complex objects. This is the kind of universe that you're likely to end up with life in. And so Smolin's argument is that because of this survival of the fittest for universes as a whole, you're almost guaranteed that any particular universe you pick out is the kind of universe that will produce lots of black holes and therefore lots of complexity and therefore will support life. And there are various other versions of this same kind of thing. And this is an attempt to kind of use the biological arguments for how you get complexity on a cosmological scale. There's a difference, of course. In the case of biology, we get to go back and look at the fossil record, and we also understand genetics so that we know how the small modifications are created. I mean, you need a set of physical laws here that tell you how different one universe is from its parents. And of course, that is not something we have any understanding of or knowledge of. And this whole multiverse concept is now getting a lot of attention from the people who worry about the philosophy of physics. And one of the arguments that people get into over this kind of thing, which is kind of an interesting one, people spend a lot of time, the people who worry about this spend a lot of time worrying about, is this science? Smolin, by the way, thinks it is. He thinks that his idea of these black holes makes a testable prediction. Namely, that the current universe should be one that produces the most number of black holes of any possible universe. So that if you imagine changing the constants of nature and doing a big simulation of what the universe would look like with that, then any other set of constants of nature would produce fewer black holes than this universe does. I think that's actually problematic because most stars in our universe don't produce black holes. So you can think, well, tweak it up so that they all make black holes. He then argues that that same tweak changes star formation in such a way that you actually get fewer stars to work with in the first place. Maybe so. Other people argue that this is totally not science because as soon as you're invoking universes other than our own, you've left the realm of science by definition. Because what is the definition of science? It's studying our own universe in ways that you can actually test. And by definition, if you're talking about another universe, it can't be tested, so this isn't science. Other people say, well, look, supposing you have some kind of a theory which predicts things in our own universe, which you can observe, and also the same theory predicts things about the multiverse, which you can't observe. If you observe the things in our universe that you can predict correctly, then that gives you some confidence that the rest of the theory might also be right. And so this is a sort of intermediate case where it's mostly science, perhaps. I have to say, I personally think it's the wrong question. Because both sides of this argument presuppose the idea that if it's science, that's good, and that if it isn't science, you shouldn't be talking about it, right? I think that's a problematic point of view. Just between you, me, and the video camera back there, it's just not true that things that aren't science aren't worth thinking about. There's plenty of things that are worth thinking about that aren't science, and my own personal view of this argument is that this is one of them, that this really isn't science, but I don't care if it's science or not because it's still pretty interesting. And I think we should also keep in mind that the border of what science is and isn't has evolved rather quickly over the past 100 years. And you know, this ought to be apparent from what we've talked about in this course. 20 years ago, talking about planets around other stars was complete science fiction. They did it on Star Trek, but not in the scientific journals. And this has now, as we saw from the example this morning, changed really very dramatically. 40 years ago, the idea that you would have black holes to actually look at, that you could pour gas into them and see what happens, was equally unscientific. 100 years ago, the idea that you could say anything scientific about the universe as a whole was completely preposterous. That was part of philosophy, not part of science. And yet, over time, all of these things have been kind of assimilated into science, and there's no reason to think that the kinds of philosophical musings about the multiverse might not also, in some way that we can't currently understand, be pulled into science. And so this whole argument over whether this is science or not might be overtaken by events. And events are, after all, moving pretty rapidly these days. This is a golden age of astrophysics because of the instruments we have, the techniques we've developed, the theories we have. You know, historians of science 1,000 years from now will say the beginning of the 21st century, that's when it was all discovered. And so it's kind of a privilege for me to play some small role in this and to have the opportunity to talk to you guys about it. And so I would say whether or not you've learned anything interesting about astrophysics and whether or not you've learned anything useful about the way science works, if you've acquired even a fraction of the enthusiasm that I feel for this enterprise, then I think our time together has been more or less worthwhile. And so that's all I have to say. Thank you for your attention, and we will meet next week.